Today's problem was submitted by a viewer, and it says, positive integers x and y satisfy the equation root x minus root 11 equals root y. What is the maximum possible value of x over y? Okay, I mean, my first instinct here was to set this up as a constrained optimization problem, but given that x and y are integers, x and y are integers, you know, a lot of the optimization techniques I'd be familiar with wouldn't work. Let's write this down and see if anything springs to mind. This might be one of those cases where I just sort of mess around. So x and y, positive integers, trying to maximize x divided by y. So of course, if we take if we rearrange the first equation, interesting that we have two square roots that differ by an irrational square root. One thing I'm considering doing, of course, we could square this to get rid of that square root and see what happens. Maybe we multiply by some sort of conjugate term. It might even be useful to do that up here. The fact that they differ by root 11 just seems kind of strange to me. Okay, I'm going to, there's no way we can figure out what root x plus root y is equal to, is there? Let's just square this and see what happens. And maybe I suppose, another thing we could potentially do is, okay, here's what I'll do is I'll write, let me take the thing that we want to maximize. I don't think this idea is going to go anywhere. Root x minus root 11 is equal to root y. And x over y is equal to root x over root y squared. So that's root x divided by root x minus root 11 squared. And now, but I've lost the fact that y is an integer here. Maximizing x over y is the same as maximizing root x over root y. Even finding integer solutions to this is not a trivial challenge. Oh, except, hold on, this gives us a hint, doesn't it? Here, x and y are integers. That means the right-hand side, x times y, has to be a perfect square. Okay, yeah, let me let's go back to here. Let's go back there and see if I can just find some examples of x and y that satisfy this. Okay, so I have x. Let's start from the beginning. This is equal to root y. Rearranging gives x, root x minus root y is equal to root 11. And squaring gives x plus y minus 2 root xy is equal to 11. So x plus y minus 11 is equal to 2 root xy. So x and y themselves will not be perfect squares, because if x and y themselves were perfect squares, then that would be an integer and that would be an integer, and we'd have a contradiction. But x times y has to be a perfect square. And they obviously have to be different, right? X has to be greater than y. Comes from this. What if I do something like x is equal to 9 times 2 and y is equal to hold on. X is equal to, well, maybe this will work. Yeah, 9 times 2 and y is equal to 2. So then xy is equal to 36. Does this work? 18 plus 2 minus 11 is equal to 9, which is not equal to 12. So whatever number x is, it has to have at least one factor with an odd power, prime factor with an odd power. And then y has to have the remaining prime factors that bring it up to an even power. Also, if we look at, I mean, that's an integer, so this is even, this number. That's odd, so we need x plus y to be odd. One of x and y is even, but not the other. Interesting. So one of them is even, but the other is odd. And can we deduce which of them has to be even? So all of the factors of 2, if only one is even, all of the factors of 2 have to appear in that number. What if x is equal to 3 cubed and y is equal to 3 times 2 squared? 27 and 12. 27 plus 12 minus 11 is equal to 28. 27 times 12 is equal to 3 to the 4 times 2 squared. Under square root, this gives us 3 squared times 2, which is 18, and 18 times 2 is not 28. Okay, I wonder if there's more. If there are more, pieces of the puzzle we can figure out, like more statements we can make like this. I don't want to just keep trying. I mean, y is equal to 2. What if we go from, oh no, if y is equal to 2, then x would have to be even. It doesn't work. Okay, what about y is equal to 3 and x is equal to 3 cubed times 2 squared? So that's, well, I'll just keep it like that. Well, I do need to compute this, the sum minus 11. 27 times 4, which is 108. Okay. And x times y is equal to 3 to the 4 times 2 squared. So under a square root, this gives us 3 squared times 2, which again, this is 18. Again, this doesn't work. Even just finding a single solution to this isn't working. So I wonder if maybe we should go about this a different way by maximizing this. As I take a limit, if x becomes extremely large, this just approaches 1. I want x to be as small as possible. Well, x has to be greater than root 11. I want x to be greater than root 11, but as small as possible. So we're essentially looking for the solution to this that has the smallest value of x. Sorry, I don't want x to be close to root 11. I want x to be close to 11. I want root x to be close to root 11. I mean, x equal 12. This is equal to 3 times 2 squared. That would require y to be equal to 3 times 3 to the 2k for some value of k to complete. But I mean, we would need this, right? So x plus y minus 11 is equal to 15 minus 11 is 4. X times y is 3 squared times 2 squared. So under square root, this is equal to 3 times 2, which is equal to 6. And we have to multiply that by 2. So this doesn't work. Make sure I did all my algebra correctly here, right? Okay, x minus 11, root x minus root 11 is y. Rearrange, square x plus y minus 2 root xy is equal to 11. Rearrange, yeah, so we need this to be a perfect square. What if I square the original expression? So I need this, okay, I need that to be an integer. So x has to be an odd power of 11 because 11 is prime. This is probably a better way to go through it. So let's suppose x is equal to 11 cubed. Then I have 11 cubed plus 11 minus 2 times root 11 and root 11 cubed is equal to y. So 11 cubed plus 11 minus 2 times 11 squared is equal to y. Can we work out what this is equal to? Factor out 11. 11 squared plus 1 minus 2 times 11 is equal to y. 122 minus 22. So 11 times 100 is equal to y. I think this has to work, right? We see from some of my work above, I'm looking for the smallest value of x that can satisfy this. So it'll have to be greater than root 11. The smallest value of x that can possibly satisfy this, if I look at this, we need x to be an odd power of 11 because this has to be an integer. And so x has to be 11 cubed. And so that's the value I get for y. So x over y is equal to 11 cubed over 1100. Well, this is equal to 11 squared over 100. So 121 over 100. And I get 1.21. Wait a minute. If I go back up to the expression here, x over y. Oh, right, of course. As x gets very, very large, this expression approaches 1. But it's decreasing. Yeah, okay. I think this makes sense. 1.21 is the largest value of x over y here. It's a nice problem. I wish I had taken the approach I did here initially. Rather than rearranging the equation before squaring, if I had squared it right away and sort of used the same logic here, you know, x and y being integers, of course, means that this has to be an integer. That happens when x is an odd, that happens only when x is an odd power of 11. And then it's just a question of also realizing, based on what the expression looks like, x over y, you want the smallest value of x, which makes this work, which of course is, I mean, the smallest odd power of x that works here will be x 11 cubed. 11 to the power of 1 doesn't work because then of course y has to be equal to 0. And the question says that they're positive integers, plus we have x divided by y, so we can't have y equal 0. It's a nice problem. I just, you know, it needs you to piece together a few different pieces of a puzzle to work out the logic of the direct way, of the shortest way there. I just wish I had squared the original expression rather than rearranging first. I'm sure I would have gotten there a lot earlier. Nice problem, and thanks for the submission.